I will tell you today some kind of overview about V8 JavaScript Engine. I'm not a contributor, but probably I should explain why I'm doing it. I want you to dig deeper when you are programming. Let's make some analogy. When you are junior developer, you write the code, you are proud of it, and when you pass it to medium or senior developer, even if you will not find bugs until he will explain what exactly was wrong there, you will not know that something is wrong. It's exactly the same with V8 Engine. Until you will know how does it work, you can't actually perform better with your code. Okay, I will tell firstly basics about V8. Later, I will focus on its components, so full code gen, crankshaft, turbofan, and ignition. Then I will switch to examples which will have some explanation why they are more optimized or anything else. And on the end, I will switch to garbage collector and how to find or just some examples of memory leaks in JavaScript. So what is V8? V8 is JavaScript engine, which is just executing your code. It's open source, but it's mostly developed by Google team. It's used in, for example, Opera, Chrome, Vivaldi, Node.js. And now let's see some most important events which were. So in 2008, V8 was introduced by Google. It was introduced with Chrome. In 2009, there is important thing that it was fastest engine these times. All others were just trying to beat it. In 2009, there was Node.js presented. It was very important for us because it shown that Node.js can be used server-side without any problems, and it could be efficient. In 2010, there was introduced first optimizing compiler, Crankshaft, which had some problems, for example, in working in parallel. In 2014, we got Turbofan, which was mostly prepared because Crankshaft wasn't working properly with bytecode, and it was time of WebAssembly, so ISM.js and so on. It was focused on such situation. In 2015, it was enabled in Chrome, and a year ago, they introduced Ignition, which is bytecode interpreter, which works strictly with Turbofan. And in 2017, so this year, January or February, it's put on A/B testing and on flag with Node. Okay. So how looks compiling in JavaScript right now? We've got three different paths. First one is interpreting, so it is faster because it can be executed immediately. Second one is full code gen, so it's just-in-time compiler, which is not optimizing anything, Crankshaft, Turbofan, optimizing compilers. And the big problem is that they can share only abstract syntax tree, which is not efficient. Everything has to be parsed differently. This year, we will switch to much more simplified compiler pipeline. So Turbofan can work directly on bytecode. Ignition will return bytecode, which is already optimized with some simple stuff. And we can get rid of Crankshaft or full code gen. So what is full code gen? It compiles JavaScript to native code. And it needs to be as quick as possible because it is the first step to run a code without any optimizations, just to make user see results as quick as possible. It's not optimizing code. Because of that, optimizations take time. And just-in-time compiling just means that there's only one function compiled at a time, because you will not use any other function meanwhile. Very important stuff is that it uses inline caches to to make code more efficient, implementation of this are called stubs. And these stubs can react on some special cases, some specific cases, which makes your code more efficient. When you call something with integer, you know that it's always integer. You don't have to check for other stuff. Crankshaft. It's optimizing compiler. The thing is that it can't work in parallel at all with JavaScript code. So when Crankshaft is working, your code will not work. It is stopped at all, and Crankshaft is just passing optimizations. Because of that, only selected functions are passed there. So when you call a function multiple times, function will be marked for optimization. Then it will be recompiled with those optimizations. And later, it will be a really optimized function. About that, there will be later some additional stuff. So also there is very important thing. It's not always is marking stuff and putting it later for later. When you've got situations like big loops, it will immediately pass a command to compiler that it needs to be optimized because we've got 1 million of operations, which needs to be performed because a code is working synchronously. On top of that, there is hydrogen and lithium. Hydrogen is, let's say, a high layer of this control flow. Lithium are just operations. Most of optimizations are passed in hydrogen graph. I will show you later how does it look. And all operations which are in hydrogen are passed to lithium. Lithium will transpile it to native instructions. One lithium operation might be just one operation for computer, but it can be also 15, depending on a machine and other stuff. So if it goes about hydrogen, it's just a control flow, which is using static single assignment form. What is actually very important when you have to pass, for example, that code. Here you get some examples. So we are using just 3 variables, actually 4, but when you try to pass it as a static single assignment, only once you can assign to one variable. As you can see here, there are just branches which are conditional on x lower than 3. It's just on the end determining what actually y should be used, the first or the second. It's determined by phi function, which is just seeking for a flow which is there. And actually compiler can beat out their second branch because it will never happen. And what it's optimizing? There are just some of optimizations. There's a lot of them, actually. And first stuff is most important, inline functions. It's inlining function, but it's performed only when it's safe and when functions are small, so below 180 operations or below 600 characters. There's a tricky stuff that comments also are counting to that. Probably you've seen it on some articles. Also, it tag values. It tag almost all values. If it goes about objects, it always gets a tag. But there is important stuff with integers or doubles, because when compilers see that it can be used as just plain integer, it will do it. Your code will be faster, as it will not pass through the whole procedure. Another thing, it's analyzing assigned integers, because in JavaScript, in memory, it looks pretty different. You've got one bit, which is a marking variable that in memory that it's another type. But we have to use bigger values also, so it has to find out this stuff and change it. Another step, canonicalization. It's just simplifying your code. So when you get a pretty big code, which actually could be performed in 3 lines, it does it. Global value numbering, it eliminates redundancy by hashing your all operations and input values. So when you perform 10 operations which are just exactly the same, it will not do it because there is no need for that. Another stuff, redundant bounds check elimination. In native code, it has to check if this array exists, if it's not out of bounds. When it knows that there will not such possibility, it can just remove those checks. And the last one here is dead code elimination, just removing code which is not needed. Turbofan. Turbofan is designed to be much more flexible. It uses sea of nodes concept, which actually doesn't care about order of nodes with operations. It needs only information about control nodes, which will change the branches, for example, conditionals. This way, all operations can be just optimized one by one without any problem. It's able to easily handle more features, it's more aggressive, and it optimizes progressively because of how it's built. It's optimization built on optimization layers, so you don't have to pass all optimizations at once. You can perform it one by one. There will be one optimization, for example, removing dead codes, another, and another, and another. So it doesn't have to optimize your function fully. It has scheduling algorithm in opposite of Crankshaft, because Crankshaft actually couldn't do that because of its design. So it's doing what I said already. It's progressively optimizing instead of doing it just once. It makes it much more faster, much more flexible. So that's why V8 is switching to this instead of Crankshaft. Ignition. Ignition, you can enable in Chrome by flag disable V8 Ignition Turbo, but also it's put on A/B testing, so probably you are using it as well. In Node, you have to use ignition flag. And how it works, it's bytecode interpreter. It was mostly prepared to make less memory usage for compiling. Firstly, because pipeline is simplified, so it doesn't have to be compiled a few times. Secondly, it's just needs less memory for that. It have to improve startup time because what I said before, it's just executing code at once. It simplifies as you've seen before, and also it has mechanisms for optimizations. So, for example, you can remove that code in this point. You don't have to pass it to Turbofan. Okay, let's switch to examples. I've prepared this test on this MacBook, so it's early 2015 with E5 8 GB, Node 7.7, V8 5.5, and time was calculated just by time system function. Number of iterations vary because I just didn't want to run the test for an hour to check if it really works. And switch to a first example, sorry. So a try catch. Many people see a try catch as not really so fast. They're partially right, because when optimizing compiler just see try catch, it can't determine where a code should go when exception happens. So in this way, running it inside of test function, you will have a problem. This function will be not optimized at all. Optimizers, actually optimizing compilers has such problems. They will probably show you a reason why it's not optimized. For example, you can look at Chrome, you will see, in this case, try catch statement as a reason of not optimizing. So we can just move it outside of this function. Now, processing function will be oh, sorry, processing function will be optimized because it doesn't have try-catch statement, and just a part which is executing this function will not be optimized, what it's not really something bad. In this case, we've got almost 15 times faster code, so it's really worth to know about it. Another example, just to show you that it's not so intuitive sometimes, we've got some function which is iterating over keys in object. This time it's empty object. It's doing it a lot of times, 100 millions of times. So one quick optimization which could be performed. Let's move key outside of function. Then we don't have to declare it 100 million times. And the problem is that it's 2 times slower. And actually, the reason of it might be a way of optimizing for functions, actually all loops, because it can make assumptions to move it to preheader state. But actually, I'm not 100% sure that in this case, that's the reason. So it's not really all the time intuitive. Let's see another loops. It's more complex example. So we've got for of, and we've got classic for, which is just iterating over e counter, and another one which is using a new syntax of for of. It's 20 times slower, I think. The thing is that for of is much more complex. There is a lot of stuff doing on beside, and also optimizer can't do stuff with it. It will throw a reason for of statement, but the truth is that the core reason is how iterables are implemented in JavaScript. So they are using generators to pass elements to for of loop. And the core problem here is that both Crankshaft and Turbofan can't optimize yet generators. There's a lot of stuff you can find on GitHub V8 bailouts, which has a list of 100 or 200 reasons. But the truth is that there is maybe 30 of reasons which are core reasons, which blocks all other optimizations. And here we've got something connected to steps, which I was talking about before. So we've got a function which is just returning number plus string. It's running 1 billion times, so it's pretty a lot. It runs for 7 seconds. And let's see another example. We are just making there 4 more operations on this 1 billion of operations, but we do it with other types, undefined, null, string, and boolean. It makes code 3 times slower. It doesn't matter that these operations are only called 4 times in opposite to 1 billion of times. It's how actually stubs work. So we've got mono and polymorphic operations. When a stub has just one case, it's much simpler to determine how it should behave to get data from memory. But when it's called with other types, there are more cases created. So a stub on the beginning will have just no cases, later 1 case. And when it misses, so the case is not a case of your code, it will regenerate stub to handle it. We've got monomorphic stubs, which just has only 1 case, and we've got megamorphic stubs that has more cases. They have to prepare some safety gates to be sure that they will not pass a value to get it from memory different ways. So you can't get object the same way as a string. Objects interpretation. Okay, so we've got a simple example that is just assigning a value to object property. The only difference is that a key is here 0 and here it's x. Time, it's just slightly different, but it's always there. And the reason of that is because JavaScript is actually using different representation of objects depending on how they work. So we've got hash tables, which are used for difficult objects that they can't work with efficiently on otherwise. They are very slow because they have to go through memory, through array objects to find it. We've got fast elements. Those are mostly arrays. Those arrays have to be also small, maximum of 100,000 of elements, and there is past every object which has integer indexes. The thing is that you have to start from 0 and so on, because otherwise it could be handled as hash table to perform on that. Another way of putting properties is fast in object properties. They create hidden classes. I will show you later how does it work. And they are sharing the same structure. Okay, and methods, prototypes. Functions are also optimized because it's very common use case in JavaScript to use prototype to pass a function. So they had to just work with it. And very important stuff is that object can move from one representation to another. So, for example, if you will have an array and you will delete some index or you will try to iterate from the end to create a new array, there may happen a situation that it will be redesigned as a hash table. It will be very slow and just in use it will be much slower than fast elements. So what are hidden classes? Let's say we've got a point constructor. Until any assignment is set, in memory it's just a point. But each assignment is making a transition. It's changing a hidden class which is beside in memory. So when we assign x, we've got another hidden class, in this case M1. When we assign y, it's M2. And when we assign a function, it's M3 here. Here we've got example how does it work in real code. So we've got a conditional in constructor, which will create a new variable, new property, only if x is bigger than 10. And we've got two instances of this point class here. So the first one has x lower than 10. So it has another map used, because after this property is assigned, you will have another structure in memory. It's not shared. And how does it look exactly in memory? We've got few parts of JS object. So there's map. The map is just a pointer to a hidden class. It will tell on which offset it should search for in object properties like A, B, and so on. There are extra properties which are mostly used by hash map, and elements which are just plain elements in fast elements array. Let's see another example. So arguments is very tricky because it's kind of magic variable. Compiler can't determine all the time how does it work, can't determine what is the type of it. So in this case, I just shown you not a real example in practice. I hope you are not using it. There we've got assigned arguments to one variable, and later we assign to it just array with one element. It's much slower than creating new variable which will be just an array because of how compilers work. So when they've got information that there's a variable which has a static type, it can optimize it. In this case, arguments is too big problem for it. So let's think about mutating arguments again. We've got arguments object where we assign to first argument 0, and we are trying to return this value. In this case, it takes 30 seconds. When we will move to assigning it to another value, which is not arguments, it's way faster. The reason is that arguments beside has to align with named arguments in function. So compiler has to perform much more stuff than it's just for a real object. If we really want to mutate arguments, let's try to assign to named arguments and return it from arguments object. It's just the same because of same thing. When you change named argument, it has to be aligned to arguments as well. When we will use only named arguments, it's just a pure function, so it doesn't make really a problem because it's not using arguments. Compiler is sure that it's safe to use it and will not cause any problems. So it's 15 times faster, I think. Okay, methods to find bottlenecks. Firstly, we should find the problems by profiler or timeline if we are using Chrome. It's mostly for front-end developers here, but we've got also a lot of methods which are connected both to V8 and just to optimizations and profiling. So when we use node with flag inspect br key or inspect itself, it will open a DevTools instance where you can just see a code. You can profile it as well, just like a normal browser application. There are another options here, trace opt, trace deopt. It's showing information about all optimizations and the optimization stuff which were performed. So you will have information that this function has been particularly took by crankshaft, and it performed this optimization on it. Later, when it will be de-optimized because there will be some problems with those optimizations, they were not so safe, it will show you any information that it has been de-optimized, and probably it will be optimized then by turbofan again. Allow native syntax, it's pretty okay. You can use native syntax which has V8 access, but it will not be highlighted in JetBrains, Atom, or anything else. These methods are starting from %sign, so the syntax is broken because of that. When you will use native syntax, you can, for example, call a function which will tell you that this function is optimized, this has some problems, so you can programmatically check out what's going on. Prof and prof process are pretty connected because prof will profile your code, generate some log file, and prof process will just process this file and show you real information which will be hard to read from a real log file. Because there in log you've got just operations one by one. Here you will have percentages, processor ticks, and so on. Here is example of such log. So you'll see that it's using some short libraries. It's taking a time 17% of time in JavaScript and also 2% time in C++. That's not full log because it was much more bigger. And here, by this information, you can see that it's compiling, so optimizing a function. In JavaScript, it's using just a little anti-DLL, and it has to clear a memory in new space, which I will be talking about soon. Also, you've got some other options. You can just run a flag v8 options for node. You'll see a list, which is pretty big. There is, I think, 100 operations, 100 flags possible to get insights of v8 in your code. So, garbage collector and memory leaks. First information is pretty basic. We've got garbage collector. Why do we need it? We need it to delete data from memory to just not run out of it. Actually, garbage collector has to be slower most of the time than managing memory by yourself, but if you will try to do it by yourself, probably in big applications you can not really perform good. Also, you may just miss something. Using garbage collector will make those problems much smaller. But the problem is that program has to stop when garbage collector is working because of mechanism stop the word and v8 garbage collector. So before current GC, there was a problem that it was synchronizable, and it could stop your code even for 1 second or 2 seconds just to swipe memory. Right now, it's performing in chunks. It can work asynchronously, almost asynchronously, so lags are just between 1 and 5 milliseconds. It's much easier to just manage memory this way. So how does it work? It's creating a graph of nodes with connections between them. That's important to just define which value is live, which is not. If a value variable is accessible from root, so from window or globally node, it means that it's live. Otherwise, it's just removed, actually deleted. There's pretty important stuff that new data is most of the time temporary, so probably should be earlier destroyed. This will be later much more extended. So actually, I will just switch to another. Most important stuff is that we've got young generation and old generation. When elements just appear, they will probably in young generation new space, what means that it will be firstly checked if it's not some kind of temporary variable like a counter. It's pretty often that we use such variables which are swept just after a function run. So after surviving a while in new space, elements are moved to old space, which is much slower if it goes about algorithm for collection of those data. But allocation there is fast, so we've got time in new space, we've got pretty small size of this space, and we have to move it to there. Okay, so we are using scavenge collection on new space. There's mark sweep or mark compact depending on paging needed in memory. Marking can be processed in chunks, so it's, as I said before, it doesn't have to stop you fully. It could be performed just in a while of pause. And we've got a free marking state. So there's a white variable which hasn't been reached yet. There's a gray variable which has been reached, has been checked, but not all neighbors has been checked yet. And there's a black one, which means that it was checked, all its neighbors were checked as well. Let's see how this works. So we are starting from root. It's already checked. We go to its neighbors, actually child nodes here. When we go to B, it's just finishing this branch because there's nothing more. We are starting a branch. We go to all variables, and we see that all of them should be alive because we can reach them. But when we remove a pointer from A to D, so let's say in property there was a pointer to D, it's really simplified because actually this pointer is in memory yet, but let's say for this presentation. So we are also going the same way, but the object wasn't reached. So let's see, it's just sweep from memory. If it goes about memory zones, new space is pretty simple. It's just a small space with 1 up to 8 megabytes of space. It's collected quickly and most of objects is collected. Rest is put to the old space. But there are few spaces which are connected to old space. We've got old pointer space. There are objects which will point to another object. Old data space which will have only raw data. So, for example, some strings or objects with objects, but still without any pointers. And large object space which will just have objects which couldn't be assigned to another space. Also, there's code space, which was a problem before ignition because there was a lot of JIT instructions. Now it's not needed because turbofan is working just on bytecode. Code objects, so the code's ready to execution. And also we've got some cells, some spaces which are just needed to make Node.js working. As I shown before, object is not really so simple in memory, and here you get example of some spaces which are used internally. So what are most common memory leaks? Firstly, you could assign to global object. It will be if this function will be in strict mode, it will not actually work. But right now, you could do it by accident. This object is leaked because it's available in global. Probably, actually, it will be just used in function. Another example, timers. So we've got interval, which will probably not go even to this console log to get this data, but we haven't cleared this data even when we don't need them. This problem also occurs in other situations like listeners. So sometimes you will have listeners which are not really needed. They have some pointers to another value, so they will not be swept. Those values also will not be swept. We should remove such cases. We should clear those variables, those listeners. Also, when you are just caching some DOM elements in JavaScript, it's just the same. Just set it to null, and it will be much better. And there's more complex example. It's based on some memory leak which was in Meteor framework as far as I remember. So we've got the thing which for now is not assigned. We've got replace thing function, which is firstly getting the old thing, which was from previous call. We've got unused function here, which is unused but has pointer to original thing. And we've got assignment to this global, to this variable the thing with some long string and some method. The problem is that if we've got two functions there, they will share the same closure. So unused function will not be removed. It has a pointer to original thing, and original thing is pretty big because of this string. And each iteration, each timer will be dispatched. We've got another object which is created and not removed from memory. So how to detect memory leaks? Firstly, most important, just generate heap dumps. So in Chrome, you could go to Profiler, or right now JS Profiler tab, and click Profile button. It will create a heap dump of data. Oh, it was heap dump. Never mind. And in Node.js, you could use heap dump module, which will work just the same. You can snapshot your memory in any time. Very important thing to find memory leak is to compare 2 or 3 snapshots depending on if there is any initialization or not. In Chrome DevTools, you can even import Heap Dump from Node, so it's not a problem. It's a pretty cool tool. When you go to Comparison tab in JS Profiler, it's much easier to see what stays in memory between those calls. So here we've got a long string from the previous example. Another way for finding such stuff, more hardcore, is using gcor, which is very standard thing. But you have to, you can programmatically find out those objects which are in memory to find what actually point to it and so on. The thing is, which is pretty important, when you see that your Node.js application is just increasing in memory, it doesn't really mean that it has some memory leak. There's max all space size, you can set it also by flag, that will, after all space will reach this size, then garbage collector will be started. It's important because, for example, on low machines, you could set up 500 of memory, but application can anyway run out of memory because of that, because it will not sweep this memory because it's really, really slow. Okay, here we've got few useful links. You can go there from presentation, which is available in internet. So we've got code mirror for V8. We've got some blog from V8 team. We've got some presentations, some explanations, and it's pretty good to just read it. And that's all.